Great, thanks for being here. My name is Jake Vanderplas. I'm an astronomer working in a computer science department right now, and I work kind of at the intersection of astronomy research and machine learning, data mining, working with large data sets. I'm going to talk a little bit about a package called AstroML that we've been working on that was released last fall, and hopefully convince you to contribute. But so essentially the background of this is the field of astronomy has been changing a lot, and when I tell people that I'm an astronomer, I think this is the image they have in mind. Edwin Hubble at his telescope at the Palomar Observatory, you know, kind of the solitary scientist looking up into the heavens, discovering truth, and then telling everybody about it, right? But that way of doing science is changing, and it's changing across a lot of fields. And what's happening in astronomy is we're moving towards doing survey-type science. So the instrument that I've been involved with a little bit, and that others in this room have been working on, is the Large Synoptic Survey Telescope. This is a project that it's a large telescope that will be built on a high mountaintop in Chile. You can see the little person standing there for reference. It's a very, very big instrument. And the specs on it are pretty incredible. The first light is going to be late in this decade. The mirror size here is 8.4 meters, so that's 8.4 meter diameter mirror looking up at the heavens. 3.2 gigapixel camera. Field of view is 10 square degrees, and this is a really large field of view. And what it'll allow is the telescope in an automated mode to scan basically the entire sky. And it'll take about 3 nights to scan the whole sky, and then go ahead and repeat that over the course of 10 years. So what we end up with is this 10-year, essentially, movie of the night sky through multiple wave bands. And the data rate is going to be incredible, about 30,000 gigabytes of raw data per night. And when you do the multiplication, at the end of 10 years, we'll end up with hundreds of petabytes of data, right? So this is much more than a single solitary astronomer looking at a set of images can deal with. And this is why we in astronomy and similar things in other fields, people are moving to automated machine learning methods and other data mining methods. So this is what we're preparing for. And in astronomy, we have a lot of statistical routines, statistical tasks, and machine learning tasks that we need. Photometric redshifts, which is a regression problem. We need source classification, dimensionality reduction. I won't read the list, but this is just the beginning of all the tools that we need to do our science and to go from this raw data to things like answering questions about dark energy and dark matter and the history and the fate of the universe, and those big questions that we love to talk about. So every astronomer needs these tools, and the great thing is that Python, we've found that Python contains a lot of these, and Python contains packages that have good implementations of these. So in a lot of projects, this is just an incomplete list of some of the projects that are out there using Python. And we've seen increasingly in the last 10 years astronomers moving toward using Python. And this is led by some of the folks at Space Telescope Science Institute who kind of put some backing behind Matplotlib in the early days and have been real advocates of the Python scientific community. And I've seen it myself. When I arrived at UW 7 years ago, there was one professor using Python in the department. And I had the good fortune of working with him. And that's how I got my start in the scientific Python world. And at the very beginning, people kind of made fun of me for being the guy who used Python instead of IDL. And it was this running joke that in the graduate classes, when I would turn in my assignments in Python, everyone else was writing them in IDL. It was this kind of running joke that I was just trying to make life hard for the professors. And over the last 6 years, it's shifted, and now the people who are still using IDL kind of talk about it sheepishly and apologetically. And we have most of the department working on Python. And that's mainly because of the LSST and these other projects. People in the department are working on those and seeing how powerful a tool Python is for that. So in the last year or so, we've developed this library, AstroML, and it's basically a set of tools and examples and data set loaders for doing these sorts of tasks in astronomy. There's a few pieces of original code in there, but a lot of it is just compiling what's out there. We draw heavily from scikit-learn, from SciPy, from NumPy, from matplotlib, PyMC, other packages like this, and pull them together in a way that they can be used and understood easily. We have about 200 plus examples on there that work with real data. You can check out astroml.org and click around. It's similar to some of the other documentation websites out there where we have plots. You click on the plots, you see the Python source code. You can download the source code, you can run it yourself, and you can retry our analysis that we did. Now, I should say the initial impetus behind this package was a book that I've been co-authoring. It's going to be released or published in January 2014. I think I was here last summer and I said January 2013. But these things tend to happen, but this January 2014 is solid. The book is written and it's just in copy editing and everything right now. So what we aim for this to be is a complete practical guide to data analysis, machine learning within the context of astronomy. But it's also kind of an introductory background to statistics for scientists. The examples draw from astronomy, but we think the book as a whole will be applicable to people in other fields as well. And it's an example-driven approach. We use lots of real data, which is available online through this AstroML package. And the cool thing about it, the thing I'm really excited about, is every figure in the book has an associated web page. So if you want to know how we made figure 4.2, you go to AstroML, navigate to figure 4.2, and you download the Python code, run it, and you can play around with the figure yourself. So I'm really hoping this will kind of be a new paradigm for technical textbooks, that we have these sorts of tools. You know, we've been hearing about open research. I like to think of this as the open textbook. And you know, a few other people have been doing similar things, and it's exciting to see that sort of direction. So I just want to run through, show you a few examples here. Everything I'm going to show here, all these plots are available on astroml.org. You might have to click through to various places to find them. But you can run all these examples yourself, and you can tweak the parameters and see what goes on. So the first data set I'm going to show you is some data from the Sloan Digital Sky Survey. This has the 3D locations of about 1 million galaxies out there. And what we've done is we've taken a little section of the sky, this place that's called the Sloan Great Wall. It's a long, extended cluster of galaxies that's about 300 megaparsecs away or so. And an interesting task that you can do with these is to do some sort of automated structure learning on it. So we applied a minimum spanning tree, a Euclidean minimum spanning tree to this that basically finds the minimum graph that connects this in Euclidean space. And then there's a form of hierarchical clustering you can do where you basically cut off the small links, or cut off the large links in the minimum spanning tree, have some sort of threshold, and then everything below that are clusters that are joined and somehow related. And this is one of the techniques that's often used in n-body simulations when astronomers simulate the galaxy and want to know about the statistics of the resulting universe that they derive in their simulations. Another thing you can do with this is density estimation. We have several density estimation tools, kernel density estimation, k-nearest neighbors density estimation. And this is just a way to, again, automatically characterize some of these observations. And then another density estimation technique is Gaussian mixture models. So to show you really quickly what the code is for this, for the Gaussian mixture models, it's really simple. We fetch the Great Wall using the datasets tools. And this will be downloaded automatically from the Sloan server and then cached on your hard drive. The syntax is very similar to scikit-learn, if any of you are familiar with that. We just do a quick density fit and then and compute the density that way. So 5, 6, maybe up to 10 lines of code, and you can do these powerful analyses and start playing with the parameters and see how things change. Here's another one that I think is kind of fun. What we're looking at here is the color plot of stars out in the from the Stripe 82 of the Sloan Digital Sky Survey. And essentially each axis is kind of a ratio of the amount of energy in one part of the spectrum to the amount of energy in another part of the spectrum. And it's a way that astronomers usually characterize objects that we look at out in the sky. And on the left is the the standard stars. So these are stars that have been observed many, many times. And because of that, they have much more precise measurements. On the right, we have a single epoch. So these are measurements that aren't as precise. They have more noise. And the way that's reflected is in this horizontal part of the plot. You can see that the standard stars that have more precise measurements, it's a much tighter sequence. And this is an interesting, this sequence reflects what's going on physically in these stars. And it's interesting because this can actually be, this is so standard across the galaxy that it can be used as a calibration for your telescopes. We know that stars are very tight in this sequence. Now, so what we've done is something called extreme deconvolution. It's an algorithm that came from some astronomers at NYU, David Hogg and his group. And what extreme deconvolution does is it takes into account that noise and fits a sum of n-dimensional Gaussians to the data. And by doing that, we can represent, in the bottom right here, we see that we're representing the data as a sum of Gaussians. And we've kind of deconvolved the noise from this. So this, on the bottom right, the representation is learned from the single epoch noisy data. And on the bottom left, if we do a resampling from those Gaussians where we've deconvolved the noise, we get an estimate of what the underlying distribution might look like. And if we kind of look at the perpendicular to this axis and look at the spread of this, the blue is the single epoch images, so we see that it's wide, the noise is contributing to that. Green has less noise because we're stacking more images and getting the errors down. And the red is what we would claim is the representation of the true underlying distribution once you deconvolve that noise. So this is a way that allows us to work with noisy data and kind of see what's underlying in a statistical sense. And again, this is an easy thing to do. We fetch the data sets using our fetchers, caches it to your disk. We prepare the data into the data and the error arrays, and then it's just a quick scikit-learn, similar to scikit-learn interface to perform the fit. So you can download this and play around with it on your own data if you like. This algorithm is a little bit slow because there's a lot going on in the background. So it won't work on extremely large data sets, but we're hoping to improve that a little bit in the future. So one last thing, and this is kind of a fun one, doing histograms the right way. You know, histograms are one of these things that almost every scientist uses when they're looking at exploring their data set. So, but there's some choices involved, right? On the left and the right, we have two histograms that are the same underlying data set. And the difference is we chose a different bin size. So the question is, what's a better representation of the data? Are we getting better on the left or on the right? And that middle spike in the right data, is that a real feature or is that just instrumental noise or a fake feature, statistical noise in the data set? It turns out there are better ways to answer this. There are a couple of routines out there that actually apply Bayesian or frequentist models to these data sets and ask what is the best possible binning to represent our data. On the left, this is a Knuth's rule. It's a fixed bin width histogram that applies a Bayesian model to basically say what's the best piecewise constant representation of my data density. And on the right is a really cool algorithm that came from Jeff Scargill. If any of you know the Lom-Scargill periodograms, it's the same guy. And this is actually a variable bin width histogram. So it uses some interesting dynamic programming. It's an interesting application of dynamic programming and very efficiently explores the entire space of variable bin width histograms and gives you the best possible results. So one thing we see here is that spike in the middle, according to these data models, is actually a real thing. And this algorithm, the one on the right in particular, has been used in time series data. In order to find changes in a light curve, where a star got brighter. And you can actually quantify that. Now you might notice there's a strange little spike in the right one right there. If you zoom in on that, you see that there's actually data there. This is actually a feature in the data that's coming out. And what this is saying, the presence of that spike is saying that given our underlying model of the data as a piecewise constant with a certain prior on the widths, that it's best represented by having a small spike right there. So in that case, you have a feature in your data that you can explore, and you can dive a little bit deeper and say, is this a real thing? Is this reflecting a new physical process in my data, or is it just noise? And this offers you a quantitative way to explore your data and see that. So again, this is very simple. I tried to make this as easy as possible. I wrapped the matplotlib histogram function and gave it instead of specifying a number of bins, you can specify bins as a string, being nuth or blocks, and it will automatically plot those histograms for you. So this is all within AstroML. And I should say briefly that AstroML is a really lightweight install. It's Python only. We also have an add-on kit that implements some faster Python code and things like that. But AstroML, you can pip install AstroML and have basically all these tools at your fingertips without much headache. As long as you have SciPy and scikit-learn and NumPy and matplotlib installed already, which I'm assuming most of you do. So really quick on the vision side of this, we're hoping that AstroML will help within the field of astronomy, will help people move more towards doing reproducible research. We already have a couple of papers that are using this code, and the figures from those papers are available online. So we can link from the PDF of the papers to the source code online that'll be kept up to date. We have coherent, well-written examples using real data. That's a real key. This real data aspect is nice for teaching. We've used this to teach both graduates and undergraduates. And the fact that they can fetch astronomical data without having to worry about the SDSS SQL interface is really helpful. And you can do, as I've shown you, you can do some really powerful analyses in about 10 lines of code. And another thing that I feel strongly about is I want to take this, we depend heavily on SciPy, scikit-learn, and I want to move some of these things that we've been working on here upstream into those packages. We've already done that a little bit. I've worked a lot on the ball tree and two-point statistics, and I've been moving that into scikit-learn. Things like the sparse graph algorithms, minimum spanning tree, I pushed that up into SciPy last summer. And there's some other things. And I'm wondering, if there are any matplotlib developers who would be interested in these Bayesian block histograms. It could be fun to include those into matplotlib as well. So that's all I have to say. This is the website. Check it out and find me if you have any questions. And thanks for listening.
Okay, we have open questions.
Yeah, back there.
First, let me say thanks for the presentation, and especially the histogram portion. It's really interesting. The question is, when these telescopes in the future come and they have these huge quantities of data, are the tools to analyze the data going to be remote, or are people still going to try?
Yeah, so the question is about these huge data sets in the future, the hundreds of petabytes. Are the analysis tools going to be remote, or are you going to have to download the data to work on them? That's something we're still working on. We're not going to be able to download 100 petabytes of data to our laptop, right? So the answer is the tools need to be remote. And there are a lot of people working on how to best do this, but the answer is not clear. We still have a few years until first light, but a few years is starting to seem pretty short given the amount of data that we have to work with. So I won't go into detail now, but if you want to chat later, I can tell you some of the efforts that have been going on in our community. Yeah.
So out of curiosity, the minimum spanning tree, are you picking the threshold manually, or is there a procedure for those pictures such that it's easy to pick out? Because it's usually a pretty difficult problem in general images.
Yeah, so the question is about the minimum spanning tree, whether we're whether we're doing that manually or learning the threshold. And this one was just doing it manually. I think we did a 90% cutoff or something like that. So.
Any other question?
One more.
Yeah, when you're showing the histograms, and you're saying that real stuff, you're saying, is that real or not? If it is used by some error in the instrument, then your basic statistics aren't going to help tell you whether it's real.
Yeah. So the question is about that spike in the histogram, whether it's real. And he was mentioning that if it's introduced by instrumental systematics, then your Bayesian model will not help you with that. And as a Bayesian at heart, I would say, well, you have the wrong model. You need to, you need to include your instrumental systematics. But yeah, it's a good point. And, but what it will tell you is that there's something there that you need to worry about. So you can go back and check whether there's systematic things that are leading to that. So.
Okay. Thanks.
Yeah, thanks.
Jake.